Alright, so this is 4-step number 12, and we're in chapter 11 now. So I'm writing it split like that, to where I'm writing it's two different things. Not much is going to be different about them. So this is a 4-step generic for the one we've talked about so far is chi-square test for independence. But then I'm going to split it and also deal with a chi-square test different people pronounce that word different. Homogeneity, somebody says it really weird. Homogeneity, yeah, I don't really care how you pronounce it, to be honest. And I'll probably pronounce it different every single time I say it. Alright, so I am going to split state completely in half. So regardless, I always start by, in general, always have to do what to some extent? Defining something. So do I have a variable to define? We have two variables, but all that we actually care about them is the variable name. So we don't have like an x or a y or a mu or anything. So we're just going to go straight into population because we can't define it within anything else. So I'm going to do the independence one first. And since we don't really have to specifically define any new variables that we're using, we just go straight into null hypothesis because we're doing a test. Well, we already wrote what this is. For independence, what's my null hypothesis? Row variable and column variable are independent. What's going to change to my alternative? Row variable and column variable are not independent. Most of the time I always write not capitals. I don't care if you do or not. It's just kind of to me to stand out which one's which. And it is a test, so I also need alpha. And then just like always, 0.05 if one's not given. I'm going to go ahead and write this one even though we haven't talked about it yet. We still have to start with population. we're not checking to see if they are independent. So we are not writing to see if they're independent. For homogeneity, what we're actually doing is we are comparing two different things and seeing if the distribution of that one thing between two different groups is the same. If I take we're dealing with categorical variables, so I'm trying to think through that. The travel method to school. No, I'm sure. I'll do an easier one. Let's just do something obvious, and let's say the weather outside and the shoes you wear. So like on different days, if it's sunny or if it's cold or if it's raining, is the types of shoes people wear different on different weather days. So like I would basically make a distribution of both of them and see if they're the same or not. Which is something we actually did at the very, very, very beginning of the year in chapter 1, which I'll bring back up in a second just to show you the connection there. So here, it is either this, if they are independent, that means that they what? What was already written on the other sheet? They're not related. So here, we're saying there is no difference in the distribution, which means they're the same, which means they're not independent, which means they're not changing. So there is no difference in the distribution of whatever categorical variable we're dealing with. Sorry, I didn't leave myself as much room here. For our different populations or treatments. I'm going to run out of room. That's treatments. So this would be like the example I was saying. There's no difference in the distribution of types of shoes worn for, it depends on how many weathers I added in here, but in general, it'll be 4 different weather conditions. Or if we just did like sunny versus rainy, there's no difference in the distribution of types of shoes worn for rainy days versus sunny days. So what's going to change, do you think, for alternative? There is a difference. Everything else is written the same. And then we still have alpha. Those, you should be able to relate those to each other. If things are dependent, then it's going to change depending on what happens. If they're not, then regardless of what happens, they're going to stay the same. So if they stayed the same, there was no difference in them. If it does depend, yeah. So if things are independent, it doesn't matter what happens, I'm going to say the same, which is lined up with the null for the other one, says there is no difference. So if they're the same, they're not going to change, there's no difference. If they aren't dependent, which is not independent, that means they are going to change, which means there is a difference.
In those two sides of the line, or
in what?
In the stuff on those two sides of the line, or just by the end of it?
I mean, like, this is essentially saying the same thing as this one because of that. And I'll show y'all a visual of this that we don't have to do for this chapter, but it makes more sense. Actually, I'll pull it up while we're thinking about it. So this ends up being an example that I was going to do today, or not do today. This is what I usually do in the notes. This is, actually, I don't remember which one's which. This one is the one that we do on the back of the notes. It talks about cocaine users and having to, whether they relapse or not, based off of different treatments. So these three different distributions are three different treatments. Do those three distributions look the same? No, those definitely look different, right? So if they look different, is there a difference in the distribution of the different ones? Yes, so we're saying this one. And so just connecting visually to what this is actually going on to what it is that we're actually testing. What this is back from chapter 1. It's just a segmented bar graph, which is doing the same thing that we're doing now, but it kind of just makes sense to see it together to kind of think about what's actually going on. I'm not going to make you do that, though, for this chapter. All right, so plan. Now, I am continuing my split right there just for method. And then I'm going to put them back together just so y'all can see that. So if we are doing chi-squared, our method is chi-squared test for independence. If we're over here, it's the other one. But that's essentially the only difference between the two is that, and it all has to do with how you gathered your information. So if I took one sample from one population and recorded both variables, then it is chi-squared test of independence. My other way, which we'll talk about in a second, is going to be the other one. So we've already started to talk about this part. What's my first condition? That's going to be what we always do. It's random selection or random assignment. We usually do what next? Normal, but it's not what we're doing today. We're doing what today? Large sample size. And how do I check for large sample size? So you would actually show what they are and then just write that they're all at least 5. So for this problem, the one that we were doing already, we just happened to already do the expected. If I were actually doing like a 4-step, I would have just waited and done it here. What's my last condition? Independent, which is actually 10% condition. That sounds weird right now. The example that we've talked about, we took one sample from one population, so we would have one 10% condition that we're checking. If I'm taking samples from different populations, like a 2-sample kind of thing, then we would have to check it for 2, which only applies to the homogeneity one. All right, so for do, we're going to have a degrees of freedom. Which is number of rows minus 1 times number of columns minus 1. We're going to get a number there. We've already found our expected counts chart. So now we need our test statistic, which is chi-squared. How do I find chi-squared? The sum of observed minus expected squared divided by expected. I'm showing you the way I want you to write this on a test. If you've got 15 of them, I need to see what they are.
Is it ABS?
OBS. Observe. You can write the whole thing out, but this is my first one of each, right? If I've got a whole bunch, I'm literally going to write it like this on my paper and not write all of them out, but that shows me that I'm doing them all. So for the example that we have on our paper on the front, it would be 51 minus 68.7528 squared divided by 68.7528. And then I would literally write plus dot 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 plus. And then what would my last one be? What's my last observed number? So it'd be 22 minus 25.8624 squared divided by 25.8624. And I could literally write that on my paper and I'm fine with that. And that's going to give me a number. If I'm running a test, every time once I have my test statistic, I now have to put what on my paper. In all of the tests we've ever done, once I have my test statistic, what do I have to put on my paper? What? And so this one is right skewed. It's always going to be here to some extent. Might be farther back this way, but it's always going to shade to the right. So draw and shade it. And then what are we going to get out of that? P-value. Which we then compare to what? Alpha. And I'm going to write conclude very generic because our null and alternative are so different. But I can just write it generic and not have to fill it in for both. So my conclude we what? What or what? Reject or fail to reject? What is it that we reject or fail to reject? So I'm just going to put that because whether it's independent or homogeneity is very different. So I'm just saying, hey, write your null hypothesis here. Why? So we're not changing anything about conclude. Which means that we do or do not have enough convincing evidence. And then what do I put there? So that way I'm not writing it specific to one or the other with independence or homogeneity.